This is Unit 3, Video 8, Periodic Trends. So when we're kind of looking at the way the periodic table is constructed, we're going to have a couple of trends that we're going to kind of see across the periodic table. The first kind of trend we want to look at is something called shielding. So it's the effect that electrons have on each other. So we know that opposite charges repel. So what we want to kind of think about is when we look at the atom, we know we can always find the positively charged protons in the center of the atom. So we know we can always find those in the nucleus. We always, Rutherford discovered we've got a densely populated nucleus. So they're going to be very tight inside that nucleus. And then we have the electrons kind of free floating around on the outside, and we find them in their different energy levels, and we know we've got different number of electrons on the outside for different elements on the periodic table. So what we want to kind of look at is the effect that the electrons are going to have on each other. So if we look at something such as boron, we're going to draw Bohr's model for boron. We know that we're going to have 5 protons. So boron's center is going to have a +5 charge, right? We're going to have all those protons in there. We're going to have 2 energy levels. So we've got n equals 1 and we've got n equals 2. So we know we have a total of 5 electrons. So in the first energy level, we're going to have 2 electrons, and then floating around on the outside, we're going to have 3 to give us a total of 5. So these electrons, remember, Bohr's model stated that they travel kind of in the same path, but we know that's not true. They're going to be traveling kind of, they have wave-like properties, so they're going to be traveling kind of everywhere all around in their energy level. So what happens when they do that is these electrons shield the outer electrons from the pull of the nucleus. So the nucleus wants those negatively charged. Remember, opposites attract. So the positively charged protons want to pull those electrons into their shell, or into the center. But what happens is these electrons right here in the middle, they're going to be spinning around everywhere. So what they do is these electrons are going to have a pull of +5 on the electrons. The protons are. So these are spinning all around. What happens is they kind of create a shield. They shield these outer electrons from the pull of the nucleus. So the protons in here don't have as much of a pull on the outer ones as they do on the inner ones. They can pull the inner electrons very tight, but the outer ones are going to have a less of a pull. So however many we're shielded by is going to, we call this the effective nuclear charge. So while these have a +5 pull, these outermost electrons are going to have a pull of +3. Okay, the reason they have a +3 pull is because these 2 electrons here are shielding them from getting pulled in by the nucleus, by the protons in the nucleus. Okay, now boron, I drew this as a very, very large molecule, which is not as relatively large as I drew it. But if you look at something such as maybe oxygen, so we know oxygen is going to have a +8 charge in the center. Okay, oxygen is also going to have 2 energy levels. Okay, we're going to have 8 electrons, so we're going to have 2 on our first energy level, and then we're going to have, actually we're going to have 1, 2, 3, 4, 5, 6, 7, 2, 4, 6, 8 extra electron. Okay, so what happens here is, while we've still got a shielding of +2 here, my overall pull is +8. So there's 8 protons in here pulling on these electrons. Well, 2 of these electrons are going to shield those outer electrons. Well, what happens is only 2 of them are shielding. So the overall pull, or the effective nuclear charge on all, I'm not going to draw on all of them, but on all of them is going to be +6. So that means this oxygen's got a much greater pull. The protons have a greater pull on the electrons because the effective charge is +6. So there's more electrons that are being shielded. So these outermost electrons are going to be pulled in a lot more than the boron ones are. So because of that, because the effective nuclear charge is larger for oxygen, those electrons are going to kind of get pulled in. So where the electrons get pulled in, oxygen's going to be smaller. Whereas boron's effective charge is +3, so it doesn't have as much of a pull on the outermost electrons. So therefore, boron's going to be relatively larger. So this is going to come into effect when we deal with the atomic radius, so how big our atom is. So when we deal with atomic radius, think of energy levels. So the more, or the effective nuclear charge, if there's a large charge, such as oxygen, it's going to be a smaller atom. Whereas if we have a small charge, effective nuclear charge, and those outside electrons, we're going to have a larger atom. So when we deal with energy levels, think of the energy levels kind of as like the shell of an onion. So as we add the shell to the onion, so we're adding energy levels, so more circles, the atom is going to get larger. So as it gets larger, we're going to have a larger molecule. So we're going to say that the larger atom. So as the atomic radius increases, we're adding energy levels. So we're going to increase as we go down the periodic table. So francium is going to be very large compared to lithium. Now we're going to decrease size as we move across the periodic table, because what we're doing is we're changing the shielding in here. So as we move across the periodic table, the shielding is going to cause the electrons are going to get sucked in closer to the nucleus. So if you look at fluorine, it's going to be much smaller than sodium or magnesium because of the shielding that's occurring. So the trend for atomic radius is going to increase as we go down, and it's going to decrease from left to right. Now this is going to get tied into ionization energy. So ionization energy is the energy that we have to put in order to pop an electron off to form an ion. So that's going to deal with atomic radius. So as we go across here and the shielding effect, so for example, oxygen has got those electrons sucked in closer to its nucleus, it's going to be harder to pull those electrons off. So it's going to be harder to pop the electrons off. Whereas for boron, where it's a little bit larger and it doesn't have as much of an effect, so it's not as big, it's a little bit larger, so they're kind of loosely held outside, it's easier to remove or to add an electron for that. So ionization energy is going to depend on kind of the number of electrons we have in our outermost energy level and how they're going to be sucked into the nucleus, whether there's a large effective nuclear charge or whether there's a smaller effective nuclear charge.